computer science at Princeton. She's also got quite a track record of influencing industry from actually working at AT&T and developing features for operating on networks that are still in use today. And so she really has a couple of unusual attributes in crossover background. Certainly she's crossed over between academia and industry, so her research is very well grounded in what industry needs. She also has a very interesting crossover between circuit switching and packet switching. And not many people are successful at both. You know, in the keynotes this morning we heard about how this fundamental new notion of separating the control plane from the forwarding plane, well, maybe it's not so new. No, it's not all that new. It's only about 100 years old. It's what's driven the telecom networks since they were formed. You have circuit switching set up by a separate control plane. When we started doing data networks, we fudged a lot because we just didn't have a control plane. So she's well grounded in both, and she brings a perspective that I think is really rare. She's young, she's got awards and prizes already, and I'm sure you'll enjoy her. Please welcome JenRexford.
Great. So what I want to talk about today is one of the grand challenges in information technology, which is the complexity of software. We all know that software is very difficult to write, very difficult to maintain, very difficult to configure, and networking is no exception. In fact, if anything, it might even be worse in our field. Routers have millions of lines of code, an order of magnitude more than the space shuttle. And it's complicated to develop, and we've seen many examples of high-profile outages caused by either bugs in router or switch software, or configuration mistakes made by network operators. This is for a real reason. The problem that's being solved is hard, and the languages we're using to write that code were not designed to deal with the kind of complexity of logic and concurrency that we face in networking. And so what I want to talk about today is technology we're working on top of OpenFlow to make it easier to program OpenFlow networks. Or we won't maybe. Okay. So what we want to be able to do is to provide a language that raises the level of abstraction for the programmer who's writing applications on top of a software-defined network, and a runtime system that takes care of the gory details of installing rules in the switches, responding to events that happen in the lower level network, and to make that runtime system fast enough that programmers would choose to use this higher level of abstraction rather than the raw languages that they have available to them today. And maybe we'll use it to fix PowerPoint next. So one thing that's, I think, very important here, and it relates to the point Scott was making earlier this morning, is software-defined networking really gives us an opportunity to get this right, to figure out how we should be programming our network infrastructure. It doesn't answer the question, but it creates the opportunity for us to answer it. And it actually already does quite a bit. So two things I really like about OpenFlow, I think are very important in managing a network, are network-wide visibility and direct control. So OpenFlow already provides both of those things to us by giving us the abstraction of a controller on which we can combine information from multiple locations in the network, and the ability to directly impact the packet handling functionality in the data plane, rather than having to invert the operation of complex distributed control planes. So OpenFlow is already giving us both of those things, and actually probably a third thing is even more important. It's giving us the ability to innovate on top of the relatively low-level interface that today's controllers provide. And that's what I'm going to talk most about today, is trying to exploit the ability to innovate on top of that low-level API to create higher levels of abstraction. And so I'm going to talk about three limitations of the existing API. And I think they're very natural limitations, because what's there now is intentionally designed to be a fairly thin veneer on top of what the capabilities of the underlying hardware are. And so we're going to see that makes it difficult for the controller to have visibility. It does have a network-wide view, but it has an incomplete view. Intentionally, we don't want it to see everything going on in the network because it wouldn't scale. It doesn't support composition. If you want to write 3 applications, one for routing, one for monitoring, one for access control, and then smoosh them all together, you have to do a fairly complicated dance to tease apart how to do that. And finally, despite the fact that you think of the controller as a centralized entity, this is a distributed system. Right? We have switches having events, packets arriving at different places and different times. And so fundamentally, race conditions can happen, even if you want to think of it conceptually as a centralized programming model. So Frenetic is going to be a language that's going to raise the level of abstraction by addressing these 3 issues And our runtime system handles all the gory details so that you don't have to sacrifice performance to get those abstraction benefits. So I'm going to go through 3 examples of those 3 problems I mentioned and show you why we need to raise the level of abstraction. So imagine the sort of hello world of OpenFlow is to write a map learning switch. People have probably looked at PySwitch already and how would you implement something like that on OpenFlow? What you're trying to do is 2 things. You're trying to learn about new source MAC addresses, and you're trying to forward to existing ones, or flood to the ones you don't already know. So I'm going to just describe a very, very simple way you might choose to implement this if it doesn't work. So imagine every time I get a packet from a new source, I send it to the controller, and the controller learns to forward packets in the reverse direction to that source in the future, and installs a rule like that in the data plane. Okay, so let's suppose host 1 in this picture does that. It sends a packet to host 2. The controller installs a rule that says, okay, in the future, if anyone sends a packet to host 1, I'm going to forward it out the link connected to host 1. Well, the problem with that is now any future packets from sources that have not already been learned won't get learned. For example, if host 3 were to send a packet to host 1, it would match a rule that says how to forward it, but the controller would never learn about how to forward packets in the reverse direction back to that source. And so the packets from 1 to 3 would actually repeatedly be flooded. So the solution here is to think ahead of time about what the controller needs to see, which is every time there's a new source MAC or a new source MAC on a new port, and what it needs to do, which is forward on destinations, and do the cross product of those things. So it has to install rules on what port the packet came in on, what source it came from, and what destination it's going to. Having to mix the part that does MAC learning with the part that does forwarding to known and unknown destinations. Now, in this simple example, this is 20 lines of code. It's not that hard to get right, although it's actually more difficult than you would think. But we can imagine more complex examples, having to think about reading state from the network and writing to the network, and the coupling between them is actually quite painful. And so the first thing we think we need is to be able to reason about reading network state separate from writing network state. And that's the first thing. Second example is a little more complicated. I'm going to walk through a little bit of OpenFlow 101 to try to illustrate why composition is difficult on top of the low-level APIs we have today. So imagine you want to design a system that does a simple repeater, the most basic routing function you can imagine, and monitoring of web traffic. So here's an example of a repeater. So when a switch joins the network, an event handler gets invoked in your favorite controller, Knox, Beacon, etc. And it's going to install 2 rules. One that forwards packets from the input port 1 to output port 2, and the other that does the reverse. So here I'm just showing the patterns the packets match on, which are just what input port they came on. The action, which is simply to forward out the other interface. And I'm installing those 2 rules directly to the switch. Okay, so that's it. Pretty simple. Now let's suppose I want to monitor web traffic, and I'm going to look at web traffic as port 80 traffic coming from the internet. And so the pattern I want to match on is that the packet comes in from the external internet, and the source port number is 80 for HTTP. I want to install a rule for that case to monitor the traffic. So I don't actually have any particular action I want to do. I just want to take advantage of the counters that already exist in the switch to count out the number of packets and the number of bytes that represent web traffic coming from the internet. And then every 30 seconds, I would query the network to read those counters and maybe print the results to the screen. Okay, so pretty simple. Now imagine I want to do both of these 2 things. That's the resulting program. All right, I can't just say, A plus B. I have to do something that's a mix of the functionality of both. So what's shown in black here are the things that derive from that first implementation I showed you of the repeater. The things that sort of forward in the 2 directions. The stuff in red is the stuff that comes from the monitoring application. And the stuff in white comes from neither of them. Stuff I had to add to reconcile which things should get precedence over the other. So I have to think when I'm monitoring web traffic, I have to have a rule that also forwards that web traffic. And I have to make sure that stuff that's not web traffic also gets forwarded and has a rule of lower priority so that I'm able to count the web traffic with the higher priority rule. So again, this is a relatively simple example, but you can already see that on more complex examples, if you want to combine lots of different functionality for access control, DOS mitigation, routing, a whole bunch of web server load balancing, if you try to compose all these things together, it's going to be very difficult. So the second thing we want is to be able to think about multiple tasks independently, write them once, use them often in composition with other related tasks. Even though in practice, they're driving one set of rules that are installed in the underlying hardware. But the programmer shouldn't have to think about that, because that's the second thing you want. Third thing deals more with the fact that we actually have a concurrent system. This is really a distributed system, even though we may think of a centralized controller. So imagine a common programming idiom in OpenFlow is that the first packet of a flow or a large traffic aggregate group of flows goes to the controller. The controller figures out what to do for all remaining packets that look like this one and installs one or more rules in the switches to handle the subsequent packets. Now, in practice, this takes time. It takes time for the packet to go up to the controller. It takes time for the rules to get installed. And in the meantime, more packets might arrive and get sent to the controller. Now, if the person who wrote the application is not thinking about that, they might implicitly assume they're going to see just one packet and kind of fire and forget. Even if they don't make a mistake like that, it would be nice if they could just fire and forget. But they can't, because more packets might arrive at the controller, and they have to make sure to handle them in a way that's consistent with the decision they made earlier. This problem compounds when you have multiple switches in a path where the rules are being installed in multiple hops along a packet's journey, where a packet may reach the second switch before the rules that were intended to be there have been successfully installed. So as a result, the second switch may send the packet again to the controller at an expense in performance, and also introducing, again, the risk of bugs if you don't handle that packet consistently. So we've been doing some studies of simple OpenFlow applications, doing some model checking to understand what kind of bugs people make. And these two bugs I just mentioned occurred in quite a few of the programs, because the program works correctly most of the time. It's just particular orderings of events, particular timings of packets, particular delays in talking to the underlying switches where you actually see a problem. So the program works correctly most of the time and then bombs out in the cases. So we would ideally like the programmer not to have to think about all of these different event orderings. So that's what we'd like to do. We'd like to be able to separate reading from writing. We'd like to be able to compose multiple tasks together without writing them over and over and over again. And we'd like to prevent race conditions by automatically applying the correct policy to the packets that erroneously end up getting to the controller. And so that's essentially what Frenetic is. That's exactly what we're doing. So I'm going to take a few minutes now just to tell you a little bit about our initial design of Frenetic. So we separate reads from writes. So the read language that we have is essentially like SQL, but customized to the needs of networking. So queries have the illusion that they can see anything they want to see in the network, and the runtime system will figure out what they actually need to see to run correctly. They don't affect packet forwarding, because again, the runtime system is going to make sure that these read queries compose successfully with any writes that are going on. And the language, though, is designed to be compatible with the fact that we really want to keep things in the data plane. So it has the kind of abstractions in it that match with the kinds of things the switches are capable of doing, like grouping packets by installing wildcard rules, or using byte and packet counters that are associated with rules. And I'll show you an example on the next slide. For writes, we want to be able to separate forwarding policy from the mechanism that implements it. This is actually pretty similar to the way OpenFlow works today, except we're going to have a layer underneath that translates the writing of policy into the actual rules that get installed on the switch, so we can compose multiple different modules together. And this is based on a concept in programming languages called functional reactive programming that views what's going on here as a whole bunch of different streams. Streams of packets, streams of topology changes, streams of measurement data, and in the future, maybe new streams of information from the end host. And we just have a library full of operators that allow us to filter, to merge, to transform, to split different kinds of streams, and allow people to express policy in terms of that. So pragmatically, our prototype now is an extension to the existing API for Python to use Knox. And so essentially, you can use our functions directly in your existing Knox programs. Although we're working on revisiting that to support other languages and perhaps a surface language of our own. So just show you that, come back now to the example I talked about earlier, about the repeater and the monitor. So here's how the same thing looks in Frenetic. So the repeater is actually not that different than what it looked like originally in Knox. You have a bunch of rules that take stuff going in and forwarding it to the opposite link. Now the monitor query looks different. It looks a lot like SQL. So we're going to select bytes. We want to count the number of bytes of web traffic. And we want to do that just for traffic entering in on port 2 using source port 80. And we want to do that every 30 seconds. So essentially we can use all sorts of patterns that the hardware is very capable of matching. So this, for example, never sends a packet to the controller. In fact, neither of these two modules do. They're actually proactive. The programmer just says, this is what I want to monitor, this is how I want to forward. The runtime system figures out the right composition of rules that will make sure that both of these pieces of functionality are implemented correctly. And so composition becomes a simple matter of just saying A plus B. As in the last box here, you just want to run a repeater and you want to run a web monitor. No need to change the implementation of either. So essentially then what Frenetic is, as you might imagine, the action is really in the runtime system. We've provided some abstractions that make it more natural for the programmer to write correct code and write it more quickly. And that consists of the query language and this notion of forwarding policy for doing writes. But the action, really, the rubber meets the road in the runtime system. Right? We have to find a way to implement this without sending every packet to the controller, or even sending all that many packets to the controller, or maybe in this case, for this example, no packets to the controller. And so we need to be able to take a query registered by a programmer or a policy registered with the runtime system and figure out what we can safely do in the switch so that we can guarantee that all the programs are implemented correctly, while minimizing the number of things that actually have to go to the controller. And because there is asynchrony here, sometimes things will get installed in the network with some delay. So some events or packets may reach the controller unexpectedly from the programmer's point of view. But the runtime system knows what the programmer is trying to do and can exercise the policy immediately without the programmer seeing it. Right? The programmer has already said they want to monitor a particular kind of web traffic or they want to forward a particular way. So if a packet happens to get to the controller already knows the answer of what to do, and the programmer doesn't have to deal with that. So that's also done by the runtime system. And our current runtime system is built on top of Knox, although there's nothing particularly fundamental about that. So, as you can imagine, then, there are a number of ways to think about doing the runtime system. So a couple of issues that come up, and they have a really profound influence on scalability of the runtime system and how well we can reason about correctness. So the simplest case is to say, okay, the first packet of every flow goes to the controller. We install a rule that matches only packets that look exactly like this one, a microflow rule, no wildcards. So that would be a microflow-based reactive strategy. And that's what our first prototype does. In part because we know it allows us to reason about correctness. We know exactly that the programs are correct when we implement with that strategy. But as you can imagine, this is not going to always be very efficient. It's going to send a lot of traffic to the controller. And so in version 2.0, which we're in the process of doing the prototype for now, we have a way of doing proactive installation of wildcard rules, while still knowing that the programs are going to be implemented correctly. Now, as you can imagine, this is fairly complicated. There's a lot of really difficult theoretical machinery underlying the version 2.0. Now, that's okay though, because we're going to do it, and the programmer isn't going to have to. We're going to try to get this right once and for all, so that the people who build applications on top of our platform don't have to worry about the correctness, and don't have to worry about whether the rules they're installing are keeping them from seeing packets or other events in the network that they need to see. And that's sort of the holy grail for us. Get it right once, and then let the programmer benefit. So we've written a bunch of applications on top of Frenetic, and some of them are sort of standard hello world kind of things like spanning tree, shortest path routing, discovery protocols, a web server load balancer, a router for memcached queries that are useful in the data center for distributed storage, a number of little security applications, and we've done all sorts of compositions of these different programs together on top of Frenetic. And so our goal here was to understand, well, how concise are the programs, so sort of a rough, admittedly clumsy measure of ease of programming. And what we see is that the programs are a lot shorter, and they're dramatically shorter when you compose them, because you don't have to actually do anything more than A plus B plus C. The number of lines is the number of lines in A plus the number of lines in B plus the number of lines in C. And the performance is competitive with programs running on top of Knox. It's sometimes a little slower, sometimes a little faster. With version 2.0, we expect it to be a lot faster because a lot fewer packets will go to the controller. So that's sort of where we're at with the prototype. So we've got a bunch of stuff that we're working on. So you can view Frenetic as itself still pretty low level. I mean, we're providing one level up on top of the API that OpenFlow provides, but there's a lot more we need to do. And the key point here is that all these things we list here, many of them are motherhood and apple pie, network virtualization, bringing the end host into the picture. What's important here is that we believe the language that we already have will make these things easier. And so I'm going to give you a few examples of that. So the first one is sort of the dual of our notion of doing read queries that you register, is to do consistent writing. So I want to transition my network from one policy to another. I want to take a link down for maintenance. I want to change my firewall rules, whatever kind of change you want to make. You don't want to worry that in the transition, while the network is stepping through intermediate states, that everything is messed up. It's a classic problem during routing protocol conversions, right? That you end up with loops, you end up with black holes. While you're changing your firewall, you're letting the bad guys in because you have to unwind some of your policy while you're reconfiguring your firewalls. We'd like to make all those things go away, to allow the programmer to say, here's the state now, here's the state I want at the end, and let the runtime system take care of doing the transitions. And this can take a lot of advantage of things that OpenFlow can do. We can tag packets with version numbers to make sure that they're consistently handled by one policy as they flow through the network, or to have a whole group of packets be consistently handled, like going to the same server replica in a replicated web service. And so our goal is to add these abstractions to Frenetic so that programmers don't have to think about the transition that inevitably must take place when you go from one policy to another. The rest of these things, network virtualization we'd like to add. Our abstractions help us here because a virtualized network needs to transform streams. A link fails in the physical network, we need to know which virtual links fail in which virtual topologies. That's really just a transformation of event streams, something that we can very naturally support given the language. We want to build network-wide abstractions, so you can think of the network not as a collection of switches, but instead as things like a set of paths, a traffic matrix, a reachability policy, and so on. Things that we can reason about and write about much more easily than thinking about every single individual switch in the network. We'd like to add end hosts into the picture, providing new data streams about performance of web servers, for example, that might guide load balancing policy. And finally, we want to think really hard about how we can distribute functionality across multiple controllers. So again, here I think our language will help us reason about what we can safely do concurrently, because we have registered in advance the queries and policies that the programmer wants, and so we can use that to figure out what we can safely partition and run either in different places on different controllers or concurrently on the same controller. So those are all sort of ongoing things. And this is as it should be, right? I think we should be letting 1,000 flowers bloom here. We're proposing one set of abstractions. Hopefully a lot of other people will do similar kinds of work, proposing different abstractions, and figure out if their abstractions are good by seeing if they really work when the rubber meets the road, when you want to do something more complicated than the toy examples that I was just describing. So to conclude, what we do in Frenetic is add some foundations on top of the low-level API of OpenFlow. Essentially innovating on top of OpenFlow in terms of providing programming abstractions. The key thing here is separating reading from writing, and a lot of what we're doing derives from that. And explicitly making it possible for the programmer to register a query and to register a policy with the network. And then a bunch of operators that allow us to deal with the heterogeneous streams of data that these networks inevitably have. And so this makes programming easier by providing higher level patterns for writing the code, by decoupling policy from mechanism, by enabling composition without modifying the code, and by preventing race conditions that, by handling them directly in the runtime system. And again, we think this also helps in making the new abstractions that are more, even higher level than these, a lot easier to build. So just to end, this is the folks working on Frenetic. It's a joint project between Cornell and Princeton. Nate Foster is a professor at Cornell, and Ralph Harrison, who's an instructor at West Point, are both here. So if you have more questions about Frenetic, definitely feel free to grab them. And thank you. Happy to take questions.
We have time for a couple of questions. One.
Bob Reichert, US Ignite. In your example where you did the hand composition, you had to go and change a priority and sort of the hide, byte, and so forth. Right. Give us some insight as to how Frenetic, approaches this in a more hidden, automatic manner.
That's a great question. So basically, what we do here is we recognize that the rule that the monitor wants is more specific than the rule that the repeater is installing. So for example, if you look here, we're installing something here that cares not only about what port you came in on, but also what TCP port the traffic is coming in on. So we can look at those kind of nesting relationships and essentially do a cross product. In this case, one isn't contained by the other, so it's a little simpler than a cross product. And we're essentially doing analysis in a multidimensional lattice space, if you will, of these different bits. Actually, not unlike what Nick McKeown was talking about in his talk. We essentially view points in a lattice space, and we can reason about the shapes of these multidimensional blocks and make sure we don't have situations where one rule is shattered by another, because a rule that is broader in scope is higher priority than it.
Question on the left.
Bob Lance, I worked on Mininet, and I have more of a comment, which is that to sort of validate this, that I found the same thing to be true in Mininet, that really the API is what matters, that enabling people to easily write applications is really sort of what's most important in software-defined networking. And to sort of unify what you and Scott said, those abstractions are very nice to talk about, but they don't actually enable anything until you have a nice, usable, wonderful API. And I just want to commend you and really say that anybody who wants to create great APIs, please do so, because that's really what's going to make the SDN App Store have 100,000 great network apps.
Totally agree.
All right, let's thank Jennifer.